We start now the fourth question of tutorial 3. Here we deal with the PCG signal or phonocardiogram. 3 recordings of PCG signals are given, and each of them they are 3 channel recordings, and they are sampled at 1000 hertz. Out of these, the first 2 are normal, the third one is suffering from systolic murmur, and systolic murmur means there is sound of that heart or murmur that is found in the PCG signal, and the patient is suspected of having pulmonary stenosis, that means narrowing of the artery that leading to the right ventricle to the lung, and ventricular septal defect, that means there is some opening in that the layer which is separating the left and the right ventricle. So, there is some hole in that. So, that is also causing turbulence, and pulmonary hypertension may be there. That means, the pressure is higher than the normal. So, all these things can cause actually more turbulence, giving rise to that murmur which is recorded in the PEC 33.dat. Now, to get actually that the PCG signal, we need to take the help of 2 other signals, the QRS in the ECG, and we use the Pan-Tomkin algorithm to detect that, and for that carotid pulse we need to find that Dietrich's notch. For that the Lehner and Röntgen's method is used, and these two helps to find out the onset of S1 and S2 in the PCG channel, and there will be some delay in this process. So, how do we compensate for the delay? So, that is the exercise given to us. So, first we start with downloading the data and that MATLAB file to read those data, and we need to keep them in the working directory of the MATLAB. Okay? We need to put them in the same directory, because that is the way the path is given in the code. So, here we see the 3 signals side by side, that at the top we get the PCG signal here, then ECG, then carotid pulse. That in the PCG signal, unless there is murmur, the S1 and S2, these two that waves, these two are not that prominent, and there will be lot of noise. So, S1 and S2 may get actually buried in noise. So, we need to take the help of the other signals, that is ECG, that QRS complex of the ECG, and the Dietrich's notch, this deep, these two, to help to detect S1 and S2. Now, how that happens? That when the QRS complex comes, then the ventricles get compressed and gives rise to that, starts the flow of the blood in the arteries, and that gives rise to the murmur if there is any constriction or if any other defect is there. So, that gives rise to the first signal S1 in the PCG. Then at the end of the compression of the ventricle, that when it is starting to relax, then to hold that pressure, the valve in between the ventricles and the arteries, they close, so that the pressure is maintained, and that gives rise to actually a small dip in the carotid pulse signal, that is the pressure at the carotid pulse, and at that time also there is some turbulence because of the change of pressure, and that reflects as the second wave or S2 wave. So, here in this picture we are showing that that QRS complex, if we use the Pan-Tompkin algorithm, we can find it out easily, and that helps to give us the S1, and that the Dietrich notch we can get using the Lehner and Rangan algorithm, which helps to find out that S2. So, that is the task we are assigned to, and let us look at that how we proceed. So, what we have taken here, we are explaining the block diagram of the Pan-Tompkin algorithm, where the band pass filter is there, followed by differentiator, squaring operation and the MA filter. And before that, before we take up these things, we pre-process that ECG signal. We try to remove the baseline drift. Here in the left, we see the ECG signal is suffering from the baseline drift, and that is removed by a filter with putting a 0 at the DC frequency, and followed by a, actually along with a pole is also there to make that signal in such a way that other low frequency components are not actually affected that much. So, we are able to remove the baseline wandering. So, once the pre-processing is done, let us look at that how we need to proceed. So, as a first part, we show all the three signals together. We read the PCG signal and we plot them in the left hand side. Here that we are taking a small part of it, that a small part of the signal we have taken for actually the purpose of plot, that starting point and end point is given, we have taken only that part, so that we can have a better plot. Okay. And sampling frequency, you know that it is 1000 hertz. So, we have used those information to make a good plot here. So, that first thing is that we need to go for that our Pan-Tompkin algorithm is to have a band pass filter, which is actually prepared with the help of a low pass filter and a high pass filter. That low pass filter here, that in this case we get that the output we are getting, that high frequency, the noises are subdued, the power frequency hum and the high frequency noise, they are subdued here, and for that Pan-Tompkin has given the numerator and the denominator. So, we have made use of that numerator coefficient and denominator coefficient and created the filter here, and we have passed that, actually that once the filter is made, we convolve that with the ECG signal to get the output, and then we have removed that mean, as well as we have normalized that signal to make it actually in between -1 to +1. Okay. So, we have shown the plot, and now let us proceed for the next step of the thing. Before that, we just show that more carefully. We have shown only the first two cycles, so that we can appreciate the change better. And let us now proceed for the last step of the band pass filter. Again we have another filter, that after the low pass filter we have a high pass filter here, and the denominator and the numerator are given here, numerator coefficients and denominator coefficients. We have created the filter direct from 2 structure, and we convolve it with the output of the low pass filter, and then we are finding that there is some transient at the beginning. So, we are de-emphasizing them, we are making them actually 1/4 of the amplitude for the first 40 coefficients, and rest of it remains the same, and then we are subtracting the mean and we are again normalizing it, okay, renormalizing I would rather say. So, that is the work we have done. So, here is the plot we get, that first we have the plot that we see that in this case that the P and the T wave they are subdued, and the QRS complex that remains to be prominent, but the shape is changed after this band pass filter. So, now let us go for the next step, that is the derivative filter, which is applied on the band pass filter ECG. So, the derivative filter is also provided by Pan-Tompkins, they have told what should be the form. So, we have created a filter that out of it, that direct form 2 filter, and pass it that band pass filter output through this new filter, convolve with this new filter, and again that same step of baseline removal and the normalization or renormalization is done. So, with that we get the cycles of that output of the derivative filter, and derivative filter output we can get that the signal waveform is much more actually changed. However, now the QRS complex that it has become more prominent and probably more symmetric than the previous one. Okay. And when we look at the first 2 cycles, we can get the change more clearly, and it has actually become like 2 sets of the ripples near the QRS complex, both positive and negative sides are there to it. And let us proceed for the next step. The squaring operation is the next step. We take that pointwise square and we normalize it again, and that with that what we get? We get post like structure, everything becomes positive and it becomes a little jagged, which will be more clear when we look at only the first 2 cycles, that we get the peak, but it is a bit jagged, multiple peaks are there. So, the question remains that which one we need to take as the real representative of the QRS complex, or rather though we are sure that QRS complex is there, which would indicate as a location, we get into that dilemma. So, we go to the next step, that is the integration. Here that we have actually that 30 that point MA filter is applied, and to apply that we need to actually pair 29(0) at the beginning and at the end of the signal, and then we have the 30 point MA filter here, and again it is normalized to keep the signal within that 0 to 1. So, with that we get the signal as shown in the left hand side. Now, what we get? This signal, what was that jagged peaks, now they have merged and giving a clean single peak for each QRS complex. So, that was what we are looking at, that we can get the unambiguously the location of the QRS complex, and that is the actually we get by using that MA filter. And when we look at the first 2 cycle, we get it more clearly, that we can see the jagged peaks clearly, and that helps us to see that after the integration how they merge together to a post. next is that QRS complex localization. We have to take some threshold and we need to find out that what is going above the threshold and when it is coming down, and then that is what we are doing here, that is what we are doing here, that it is above the threshold. The threshold is nothing but the mean of the that ECG signal, and that again a scale is given. Okay. So, we have taken the max, that means the 50% of the that ECG signal should come, because we have already taken this as a 1. Okay. So, we are just taking a threshold, I think it is better to tell in that way, and we take the that differentiation to find out that when we are getting 0 to 1 transition and 1 to 0 transition. Okay. And these two transition gives us that when our actually QRS complex is starting and ending. Okay. So, in between these two we have the R wave, and next what we do, we need to do some compensation of these two, and we see that we have taken a actually offset 6 plus 16, out of which the delay 6 is coming because of the low pass filter and 16 is coming out of the high pass filter. Now, how do we get it? If we want to know, we need to look at that this low pass filter and high pass filter again, that we need to find it out, that the low pass filter what we have taken earlier, that it is giving us that this signal which is giving a delay of 6 here, and that is the reason that we need to give an offset to actually remove that. Next, if we look at the high pass filter, again we see here is a 16 point delay. Look at the numerator structure, that it has that in the numerator 33 coefficients are there, which is giving a delay of 16. So, that also caused a delay in the output. Now, if we want to find out the location, we need to compensate for that. So, that will help us to go to the real place where the QRS complex was there. And next we look for the maximum point between the 2 points of x and y, which gives us the R. If we go a little backward from that ECG, or rather R point, we look at that the location of the R and that the minimum point where it started, that is xi. So, we get the Q point, and if we want to look at that y position, rather that S location, we need to look at that in between that here that R and the y. So, these three we need to look at, and here we are having an offset that each of these case, as our interval is in between xi and yi, we are looking at that the point that in that the value what we get here, it is within this range. So, we need to take care of the fact that it has xi minus 1 so many actually points before that. So, we need to add that offset to adjust that part. Okay. And here we are showing that step by step that how we are getting that output. We are showing the first 2 cycles, that to make it better, that we get the ECG, band pass output, the derivative one, then we have that the squared output of the integrator, and at the end the QRS, the complex, that Q, R and S, all the 3 points, they are marked on the ECG. Okay. So, the first 2 cycles, they make it more prominent. Next, we go for the Lehner and Rangan's method to detect the diatonic notch. So, first we remember that what are the inputs we are given, that sampling frequency, it is 1000, that we have that a filter which is 8-point filter, that order is 8 and cutoff frequency is 40. So, that it is a low pass filter with cutoff frequency 40, and we design that filter using that 3 dB, that bandwidth and the model order that of the Butterworth filter, that we create that first the design, then we create the Butterworth filter out of that 840, and we apply that on the carotid pulse here, okay, filtering the carotid pulse with that low pass Butterworth filter, and at the end of it, that we get the signal, that we remove just some unwanted portion, that we are keeping that 34 to end, that part. So, we are removing some initial part, that which is having the transient, and then we go for the plot of the signal. Okay. So, after the Butterworth low pass filter, we get the noises present earlier which were visible here, they are removed. So, that is a good thing, that we could get rid of those noises. So, that the first task. Next is that we are going for differentiator, and in fact, that it is necessary before applying a differentiator, we need to do that low pass filter, otherwise those noises could be magnified and have an impact on the accuracy of the technique. So, in this case, a second order filter or second derivative is suggested by Lehner and Rangan, and for that we do some padding. How the padding is done? Our signal is starting from say x 1, okay, to x 1, then x 2, going up to say x n minus 1 and x n. With that, we are using the reflection to pad both. We are having again x 1 and x 2, and at the end, after this, if we look at that, after this what we are having, x n plus first x n and then followed by x n minus 1. So, you get it here. So, that is the way we have increased that length, that to give it the maximum smoothness there, because if we pad with 0, it will unnecessarily give rise to some high frequency at that point. So, we have that output here of the differentiator followed by the squaring operation, pointwise squaring operation, and then we plot that signal. Okay. What we get? That we get all the signal has gone because of the differentiator, we get some pulses here, and after squaring operation that becomes positive, we get some small pulses there, and next we apply a moving average, a MA filter is applied, and that moving average, it makes it more easy to get these peaks, and to get that we have to again plot these to the scale properly, and what we get, two peaks are there for each one of them. Out of these two peaks, the second peak is important to us in each case. That second peak we have to look at. Okay. So, that the plot of the moving average we have actually given here, that after the MA filter, that we are seeing it, and we use the peak detection algorithm, find peak which is above the threshold we are looking at, and that with that we are finding out the dielectric notch which is within 20 milliseconds of the peak. Now, after finding out the second peak, what we are doing, we are going into the dielectric notch, that is the carotid pulse signal. We are looking into that and trying to find out a prominent dip, that is the pixels which are that plus minus 7, that they are above this actually point. Okay. So, we are trying to find out the point that both the side there is a actually at least 7 points, they are actually above that point. So, that way we would get not a local peak, but we will get a prominent one. Okay. So, that is how the peak we get, and then once we have the carotid pulse detected, we mark that here in this plot. Now, we are plotting the QRS and the dielectric notch which are required to do this job. Here we are showing that at the top we have the PCG signal. The PCG signal, we are showing that we are showing the location of the R which can give us the S, that R wave is here, and the carotid pulse signal is marked here, that we are marking here. So, that is giving the location of the S2 point. Okay. So, that is the way we find out the location of S1 and S2. And so, what we get, that we need corrections for compensating for the delays used for the two techniques. Pan-Tompkin algorithm, we have two filters which are giving rise to sufficient amount of delay, that is the low pass and the high pass filter. They are giving the delay of 6 and the 16 delays respectively. So, that 6 plus 16, 22 delays we need to subtract to adjust the QRS location in along with the signal. Again, for the dielectric notch, it is located by that finding out the minimum in the carotid pulse within 20 millisecond interval around the second peak. So, there also it is not exactly aligned, we need to search for it and find it out, and then only we can find the carotid pulse signal, and both of these carotid pulse, that the dielectric notch and our that location of the R wave, they help us to find out S2 and S1 respectively. Thank you.